Hello, welcome to my talk. This is Bedir Tekinerdogan. I'm affiliated with Wageningen University in the Netherlands. I'm the chair of the Information Technology Group. We are doing research on smart systems and in particular in the life sciences domain. My talk today will be about digital twin-based architecture for smart farming or precision farming. The main application domain is smart farming, but I will address also the topic from the architecture design perspectives and the notion of digital twins. Okay, so if we look at the digital twins, in essence, we can say a digital twin is a model. I will elaborate on this a bit more in the next slides. But if we talk about models, in essence, we can identify three different types of models. And models are used a lot in engineering. And the first category is a sketch, which is a simple drawing or informal drawing, which is not that precise, but it's handy for creating ideas. Then next category is a blueprint, typically used in what we call a model-based engineering. Here we develop more detailed design models, which can be handed over to developers who can then build the system in accordance with the blueprint. The final category is executable model, which are models that can be automatically generated in more refined models or documentation or code. These are the models that we know. The last one is in particular used in what we call model-driven development, in contrast to model-based development, which is the case when we use blueprint. So, but what's the situation with models so far? We use plenty of models in engineering, and also in the we are also quite successful. So there are many different kinds of abstractions and modeling notations. But the point here is like that once the models are developed and the product or the system is developed based on these models, we lose the connection with the delivered product. Hence, the monitoring, the control, and the analysis of the product is more difficult. This is changed in the case of digital twins. A digital twin can be considered as an executable model, but it's a digital replica of another twin, which is called a physical twin. Well, the digital twin is connected to the physical entity, often in real time, and it senses the state of the physical object and provides what we call rich representations of that physical entity. In that way, it can monitor, control, observe, and do some simulation of the physical object, and thus support the smart decision-making process. Well, a digital model can be used in the complete product life cycle, starting with the design, the realization, usage, and the retirement. So in essence, we can say we just keep the digital twin, and of course, in the initial case, but also once it has been delivered, and thus it can help to monitor and control the physical object. So, well, if we summarize the overall notion of digital twins from the perspective of modeling, we can have this figure. So initially, before the real mature engineering, we had just we developed a physical object, but without the use of models. When things became more complex, there was the need for a drawing. It started with sketches, and then later on, blueprints were used, and more recently, in the recent decades, generative models or executive models have been used. Well, digital twin can be seen as the next stage of modeling after the executable models, in the sense that it It is an executable model, but it keeps the connection with the physical object. Well, how can this happen? Well, it's of course part of the overall story of the digital transformation, which started with the digitization, with actually the third industrial revolution or digital revolution, uh, where we actually started to digitize documents into electronic formats. And then the next stage is the digitalization, where we actually where more digital solutions were invented that could be used to actually to create a new digital solution. And finally, this whole process led to a digital transformation, which actually had a disruptive impact on the society. Of course, these figures are like this was possible. The whole digital transformation is possible because we have now more powerful computing, more storage is possible, it's cheaper, it's smaller, and this all has actually resulted in what we say pervasive computing or ubiquitous computing. So computing is everywhere. And within this whole story, uh, we can also see the role of digital twins. Now we have pervasive computing, but digital computing, digital twins can be used to also control these different physical entities in the physical and in the physical domain. Digital twins can be used at various levels, including the component level, system level, and the process level. Component level, you just check a specific component and monitor it. But the digital twin can be also used for a complete system or can be used for optimizing, monitoring the process. The topics that I discuss in this talk have been derived from these two papers. One is on the right is based focused more on the developing ontologies for digital twins, and the left part is more focusing on developing architecture design pattern catalog for developing digital twins. If we start, we say like architecting for digital twin-based systems. What is the conceptual architecture? Well, the conceptual architecture behind the overall digital twin-based systems can be considered as a control system. So we have a physical object that is actually monitored using sensors, and the data of the sensor is provided to the so-called comparator element, which is actually checks the initial goal and provides the delta, the difference to a decision-making entity based on which the required command or action is decided, and the actuator or effector actually changes or controls the physical object. In a sense, so we could say, well, the digital twin-based system is also follows this higher level control system architecture. And we know where there are like control system, you have different examples like in like these smart thermostats, smart cars, smart houses. They are all examples of control systems. For digital twin based architecture, we can see this situation. The physical object space is the physical object or physical entity. Uh, uh, Typically includes sensors which can actually check the state of the physical object, and there are actuators which can adapt, adjust, or change the behavior of the physical object. The sensor, uh, the data is provided to the digital object with a so-called digital object adapter. And here again we have the comparator element, which is used to provide the delta, and it decides on the command. As we see, so this is a control architecture, but here we have divided the different elements over the physical object space and digital object space. Well, there are some terms that we need to know if we talk about digital twins. The physical object or the physical entity is the real world artifact. Virtual object or the digital object is the digital representation of the physical object. We have a physical environment and a virtual environment. The state of the physical object. The realization, that's the act of changing the state of a physical or virtual object. Metrology, the act of measuring the state of these twins. Twinning, the act of synchronizing the state of the physical and the virtual object. This could be based on the real time or not, and so that's defined in the twinning rate. Physical to virtual connection twinning or virtual to physical connection twinning. So it can be the twinning can be based on both sides. Well, digital twins in systems engineering. This is a meta model which defines the separate different concepts. Systems engineering builds a system. Systems engineering adopts a life cycle, has life cycle stages, and digital twin based system is a system, but it has a digital twin and a physical object, and these two should be synchronized. The digital twin based system has an architecture which is designed using architectural patterns, and system architecture digital twin patterns are architectural patterns. So in the next slides, I will focus on these system architecture digital twin patterns. What is a design pattern? Well, design pattern is just a generic solution to a recurring problem which occurs in some context. The idea is quite popular in software engineering and also in systems engineering, and several design patterns have been introduced in the literature. Here is an example, the layers pattern, which is typically used in, for example, large-scale software system where you can identify different abstraction levels of these different modules. So, and which has like this pattern says like decompose your system into so-called layers, and let these layers, the lower layers, have the more a lower abstraction level, and higher layers the higher abstraction level, and let the layers just allow to access just the next lower layer. And so no layer bridging is, so the so-called layer bridging is allowed, and also no callback. So this is typically an architectural pattern which is used in many systems. So what we will focus on is a new type, a new set of patterns that we have identified in this paper, and we have documented these patterns using this template. So each pattern has a name, has a life cycle, has a context, a problem, solution, a structure, and dynamics. Well, in essence, at the very conceptual level, we can see there are four different types of relations. If we take the digital object and the physical object, and we can look at the data flow that can be manual or automated. So if we take then there, in essence, then we have like four combinations. It can be totally manual. That is like you have a digital object or digital model based on which you actually develop the physical object. Or you could have a digital object and you could have automated data flow or automated generation. Then it becomes like more model driven. You could have also like physical object. You could reverse engineer and then build a digital model. Or you could have both relations. You could have like a digital model, you automatically generated that, and you can have also automated generation or development of or reverse engineering of a digital object. Well, what we did was like define the more precise digital twin patterns, and we have like identified 9 different digital model patterns, digital patterns. This is the first one. So we show here, as you see, both the static model and the dynamic model. In the static model, we have digital twin, which can be have different kind of concrete digital twins, which has like interface blueprint. And in the dynamic model, we show like for digital model pattern, based on a digital model, a physical object needs to be created. That's the problem that is addressed in this digital model pattern. Well, the client says get the blueprint, and the blueprint is provided, and based on that, the model is developed. The digital generator pattern is another pattern which focuses on the automated generation. That's all based on a digital model, a physical object needs to be generated. So the client here says like generate the physical object, and based on that, the digital twin is actually a physical object is generated. So the distinction with the digital model is like this is now more generation based, while the previous one was more manual. Digital shadow pattern for a given physical object, a digital twin needs to be developed, right? So now we say like you have the physical object, and based on that, develop a digital model. So the client says to the physical object, get the state, you get the state, and based on that, a digital twin is developed. The digital matching pattern based on a digital model, a physical object needs to be found, right? So you have a digital model or digital representation, and then you have to check, for example, like machine vision. You have to check whether you can find a similar physical object. The digital proxy pattern, the proxy pattern is well known in the design. It's an existing design pattern in the design pattern and software design patterns. Here we use it. A digital twin needs to act in case of a physical object. In essence, it's a special case of the general proxy pattern, but now the proxy here is the digital twin. Yet another pattern is a digital restoration pattern, in which a physical object needs to be restored to its earlier state. So that is like the digital twin keeps the state of the physical object. So you save the state to the digital object, and once there's some, for example, a failure, you can say to the digital object, restore your state, and based on the state of the digital object, the state of the physical object is restored. The digital monitor pattern, here we come enter in the control system, is a physical object needs to be monitored. So there's now close connection between the digital object and the physical object. The physical object has sensors, you can get the state, and the digital monitor continuously checks the state of the physical object. But that's all. It does not has it does not change the behavior, the state of the physical object. It's just monitoring. The control parts for the really change is done using the digital control pattern. If that's the problem that is needed, a physical object needs to be controlled, then it actually monitors, senses the physical object, and then it also changes the state. So you have a different state, the static models and different dynamic models here. The final digital twin pattern is digital autonomy pattern. Here, the control is completely done automatically by the digital twin. It automatically checks the state of the physical object. It automatically decides on the action and automatically changes the state of the physical object. Typically, hereby it also learns how to behave. Well, these are the summarizing these digital twin patterns: the digital model, digital generator, digital shadow, digital matching, digital proxy, digital restoration, and three more: the monitor, the control, and the autonomy. So each of these patterns can be used for different projects and different problems. And we have actually applied also checked, it's first checked to which life cycle activity it can be applied. This is the slide that shows it. So the digital model shadow and generator can be used in the concept state, in the utilization stage and the support stage. These patterns, in the retirement stage, we could say we could have a digital proxy pattern, which could actually live further after the retirement of the physical object. We have applied and checked these digital twin patterns also to real case studies, 3 case studies: arable farming, dairy farming, and more greenhouses, and check. This was a retrospective study, and we checked how these patterns had been applied to this project or could have been applied. As we see, like that, so basically digital shadow, digital matching, proxy were used a lot, more often, But digital autonomy we could not find yet, because that requires a more fully automated situation of the digital twin. Well, that was my talk. It was a bit longer than it was expected, but thank you for your interest. If you are interested in this topic, you can check the papers that I've shown in this paper and download it. You can also access this through my ResearchGate account. Thank you for your attention.